Welcome! In this video we will be solving the brainfuck, from now on referred to as BF challenge from Pwnable. We will see once again why it is problematic to neglect bounds checking on user-controlled data. Let's begin by reading the problem statement from Pwnable. It appears that we have a BF interpreter which currently lacks the capabilities of open bracket and close bracket. To me, this was very strange. I had no idea what this all meant, so I went ahead and downloaded the binary for analysis with the interactive disassembler. IDA Pro shows there are two interesting functions for us to analyze. We have main and doBF. Let's look at main first. So to keep things simple, we just focus on local variable assignments and function calls. The first assignment is here. It is to a local variable at ESP plus hexagon C, and its value is set to EBP plus argv. So that appears to be argv is the argument value passed to the function. If we try to cross-reference this here, we see that there's really nothing that uses argv, so we ignore that for now. The next assignment is to a local variable high up on the stack in the main stack frame. We have move ESP plus 42CH, and the value is offset hex 14 in the GS segment. So what is this used for? Let's try to cross-reference it, and we see that there is something down here. Let's take a closer look at what this segment does. We have a move 0 into EAX, and then we have move the value at, or the local variable into EDX, and then we exclusive OR this with the value at offset 14 in the GS segment. So theoretically, if nothing changed, which it doesn't look like there are any other uses of this local variable, exclusive ORing anything with itself will produce 0. So indeed, we have a conditional branch if 0, and we skip right across this address if nothing changed. In this address, or this instruction is called stack check fail. Stack check fail probably is something that will basically not let the function return. It's basically to prevent things like buffer overflows that will control the return pointer. So from this, it's probably telling us that what we're looking for is not probably a stack buffer overflow. And if it's not, because if it's not 0, in the case that this local variable is edited, then we have a call to stack check fail. All right, moving on, we see that we have two calls to set vbuff. One of them is for the standard out stream, and the other one is for the standard in stream. These aren't particularly important right now, so we just move on. We have an interesting assignment here, move ds at p at offset tape. So not sure at the moment what this is for. If we try to look at what tape references, we see that's in the BSS section, so it's uninitialized data. And also, P is also initialized, but now it's initialized to the address of tape, so it points here. We have some puts calls, so welcome to BF testing system, type some BF instructions except open bracket, close bracket. Then we have a mem set, and the mem set here is called with the value of 0, and the buffer is at ESP plus 2C, which we see there's a couple of references that later on. So probably this sets 0 to this buffer here, and the size is 400 hex, so that's 1024 bytes for this mem set. And then unsurprisingly, we have a call to fgets. To write to this buffer that we just cleared. You can see we can verify that this fgets is safe and probably will not result in possibility for overflow. Alright, now we're done with this big chunk here. Actually, we have one more assignment of 0 to ESP plus 2, 8. And then we're done with that segment. So let's look at this small node here. The node first compares this value, which is initialized to 0, with the length of the buffer that the user supplies. Remember, this was the ESP plus 2C that we saw earlier. Then they're compared, and if EBX, or if the value at ESP plus 2.8 is larger than the length, then we have this exit procedure. We have the check, stack, check, fail, blah, blah, blah. Otherwise, the value at that ESP plus 2.8 is added to ESP plus 2C, and then that is used as a pointer to move in some data, which is then called with do bf. And then after following the call to do bf, we have an increment of ESP plus 2h. So from this, it's pretty reasonable to kind of conjecture that ESP plus 2.8 is an index of some sorts into the buffer at ESP plus 2C. And in that buffer, because we see here that there is a byte pointer of EAX. EAX is the sum of the base of that user input and the index. That we call do BF on every single byte in the input. Alright, so now it obviously makes sense to check out what do BF does. Right. Immediately we see that there's an interesting geometry to this flowchart that is generated. So this type of structures, it's a lot of small segments here, and they all end up in this part, which appears to just return in the default case. You see IDA has identified it as the default case. And so this tells us that this is probably some sort of big switch statement that's going on. But let's take a closer look. So what happens first, all these instructions here, is just basically moving the argument to do BF into the EAX register. Then EAX is decremented by 2B, and then it is compared to 30, which is 48 in decimal. If it is above, in other words, if it is greater than 48 after being subtracted by 2B, we have a jump here to the default case, which just returns. Otherwise, if it is below, the offset from 2b is first multiplied by 4, then that is used as an offset into this segment here, and then we have a jump to that location. So that's pretty reasonable for a switch statement. So let's take a look at what this contains. Indeed, we have a bunch of addresses here. And so, let's go back and let's take a look at what the first case is. First case is located at 80485FE. Let's look at the jump table. 80485FE, right here. And if we count up, 5, 6, 7, 8, 10, 15. You see that it's 19 bytes above the beginning of this jump table. So 19. Remember, the argument was first decremented by 2b, so we add 19 to 2b. 19 is in hexadecimal is 13. If we add that to 2b, we get 3e. In hex. So remember, this came from user input from standard in. So what kind of ASCII value would it represent then? You can easily just look up an ASCII table here, and we see that browsing through 3e is the greater than sign. So this switch statement is executed when the byte is a greater than sign. And in the case of a greater than sign, we first move this ds at p, which we saw earlier, initialize the tape, into EAX, we add 1 to that, and then we move it back. So basically, this p is incremented by 1. Moving on, we see that for the second case, we have 804.860D. We look back into this jump table, and we find that it is located here, exactly 2 bytes underneath what we had for the first case. That leads us to conjecture that the ASCII value here is actually 3C, which is a less than sign. So that means that this block of code gets executed in the case of a less than sign. In the case of a less than sign, the value of the P is loaded into EAX, and then EAX is decremented by 1, and that's moved back again. So P is basically decremented by 1. So we can see the difference here. If we have a greater than, or, well, probably better described as a right-pointing arrow, P is incremented. If we have a less than sign or left-pointing arrow, P is decremented. This is getting curiouser and curiouser. The next few cases, we can see 804.861C. If we go into there, 804.861C. Oh, actually, it's the first value, so it's 0, no offset. And 2B, if we look in here, is a plus. So if we have a plus, what happens? We will have DSP moved into EAX, and then EDX moved, and then we have whatever is pointed to by this loaded into EDX, and then increment by 1, and then moved back into that pointer. So from this, we can probably assume that P is some kind of pointer. Whenever we do plus, that value that P points to gets incremented by 1. If we want to go to the left, we use the less than, right, the right than. So this is starting to make a little bit more sense. Let's look at the next one, which seems to subtract 1. I would not be surprised if this were a minus sign, but let's just check. So 804.862B is right here. That's located 2 bytes above. We go to here. 2 bytes, or 2 above that is indeed a minus sign. So we are correct. Okay, and so we have minus is to decrement the value pointed to by P. And remember, P starts out at tape. And tape is this long, uninitialized BSS segment. Okay, what about this? So we have 804.863A. This is here. And if we look at the ASCII, it should be just one next to minus. It's a dot. So what does a dot symbolize? A dot symbolizes, what looks like here is actually called put char. So we are displaying the value that is currently pointed to by DS at P. So whatever is pointed to by P is displayed. 804.864F is here. So it's just 1 byte above plus. It's a comma. Okay, so what does a comma symbolize? Comma symbolizes a get char. So a character is read from the standard input and loaded into whatever is pointed to by P, the byte pointer at P. This is getting pretty interesting. So essentially what we have here is we can control where P points. We can also control the value at where P points by incrementing and decrementing, and also reading and displaying it. So this already gives us kind of, and keep in mind that here, when we increment and decrement the pointer, there's really no bounds checking to this. We can increment it and decrement it wherever we want to. We can really easily exploit the system here. And finally, we have this thing. It doesn't look too important because it doesn't appear to do anything except display a message. Bracket and bracket are not supported. So this is presumably a bracket. In this case, it doesn't do anything. It just nods and exits. All right, so this is starting to look a lot like some sort of Turing machine tape engine-esque mechanism. So again, like I said before, we have complete control of a pointer. that I guess is supposed to be just limited to tape, but you really can make it move anywhere. So let's figure out an exploit for this. One thing that immediately comes to my mind is kind of writing some shellcode to the tape, and then thereafter somehow going and editing something, for example, right here in the procedure global offset table. We can make it point to tape and then start executing instructions off of tape. Our shellcode that we write for tape. But then we realized that it is in the BSS section, which of course is not executable. But no worries, we do have control over the global offset table. So if we can somehow find a way to cleverly overwrite functions that will allow us to, for example, call system on the string binsh, then we're all set. We have to figure out a way to do this. So let's go back into the disassembly and figure out what we're going to do. So the first thing I want to point out is that we have to, for system, we have to pick an instruction that takes a pointer as an argument. So for instance, puts would be an option here. However, these values seem to be hard-coded in these pointers. The values or the strings of these pointers seem to be hard-coded. So we really can't take advantage of that. And we have options like getchar and putchar, but we really don't want to edit those because we need those to kind of control what we're doing. Except for putchar, we can kind of exploit because we don't really have to read anything, not that I foresee at the moment, besides maybe an address of a procedure in the global offset table. But after we read that, then we should be free to use it. However, we have to be able to both control and execute the string for system, because we have to first write binsh. So we have to look elsewhere for this. And one natural place to look is in the main function. And let's just, looking at this first block, we see set vbuff probably won't work because, again, this is also hard-coded. But things that take local variables, for instance, this memset here uses a local variable as its argument, as its pointer, a local variable, a local pointer. So if we can somehow replace memset with something that can read into this, like for example gets, and then after this we see that fgets also uses this exact local point. This seems perfect. We can overwrite fgets with system and memset with gets, so that we can essentially, and then gets we can put in something like binsh, and system will just turn our thing over. Sterling also takes argument, but keep in mind that anything that has to do with the do-bf mechanism we really want to keep intact, because this loop has to run for us to really get anything workable. Okay, so that is going to be our exploit strategy, is to somehow overwrite the global offset table with addresses for, first of all, main, second, gets, and third, system. But how are we going to execute main? What instruction are we going to replace? Well, we can go back to do-bf, and remember I mentioned putchar. We can just replace putchar with main, and then just execute our malicious craft by putting a period or a dot into our input to our bf. And our input has to be one long string. It doesn't seem like it's a line-by-line interpreter, so we have to, everything has to be set before we get going. So, alright, so let's go ahead and just record some stuff, and then we can start exploiting. So open up Notepad. Hate on it all you want, but it's great for storing information that we need for reference. First thing we'd like to do is get the address of main, because that is something that we we need to overwrite. So main is going to be, actually let's go ahead and just pretend like we're already writing the Python script. Main is going to be equal to hex 0804 8671. So that's main. The next thing we want to do is capture the address of our pointer. We need to edit our pointer and make it go places. So we need, and the pointer starts at tape, so we probably want the address of tape as well. So let's go ahead and set tape equal to what looks like 0804.0.0, and then after this, we wanted to edit the global offset table, so we need to get the addresses from the global offset table, which is right here. So in Python, we can actually make this a little bit more accessible by just making a dictionary that will link values, or link the function name to the address in the global offset table. So we begin with, first thing we need is fgets, which is here. This looks like it is at 0804 AE010. We also need memset, which is 0804 A02C. And finally, we need putchar, and putchar is at it'll be at OX0804 A030. So these are the three PLT addresses that we need. And then after that, I think that's all we need. I don't think we need anything else for this. Alright, so let's go ahead and open up a Linux terminal to get started. So here I have my handy dandy Linux terminal, and I have the BF and bf.so libraries downloaded already. So first, let's go ahead and just go into Python directly. We call it bf exploit. So for any pwn, I'd like to use the pwnable library. It's very convenient. And the first thing we want to do is go ahead and load in these constants that I defined previously. Right. So, okay, we have the values of the addresses that we want to write to, but we don't know what we're going to write. Remember, we wanted to write main, so we have that, but we also wanted to write the address of gets and system. We don't know the addresses. How are we going to find that? Well, one thing we have is that shared object library. And to use that shared object library, we can read that with elf and get the offsets of various functions from the libc base. So to do this, we will first read it in, so that, remember, it was bf libc. And then to get the offsets, we just simply do libc.symbols and then the byte array, character array of the function name. So we need to overwrite with, let's just call it offset. We want to get the offset of gets. Gets and system are not available in the binary example itself, so that's why we have to kind of work by offsets here. We have to use libc, we have to go to the symbols, and in Python 3 it's byte array for some reason, no big deal though, and we need system C. Right, there's our offset. But how are we going to get the absolute addresses from the offset? Well, we need some reference value, some reference function or address. And that reference we can get just from one of our existing functions. So for example, in the PLT, we have fgets. So we can read in the absolute value of fgets using that convenient dot operator in the BF language, and then we can subtract off its offset in libc, and then that will give us the base of libc. So let's go ahead and also add a entry and offset for fgets. Okay, so this is all we need. Alright, so now let's craft our input, our payload. So the first thing we want to do is navigate from our tape, which we're currently at right now. Let me label that, just for clarity, to fgets. We want to go there first to read its address so we can get libc's address. So to do that, we have to use the left. We have to move the pointer down. And instead of doing that manually, I want to write a function to do that. So def, let's say move. We're going to move from the current to new. So current is the current address, new is the new address. So obviously, current could be less than new, or current could be bigger than new, and we would have to move to the left or right accordingly. So we can easily implement that. So first, let's do p, or just do variable x, current minus new. So if x is positive, so current is bigger than new, in other words, then we need to move to the left. So move to the left, and how many times? Well, it's just p. And else, we're just going to turn moving to the right. Actually, we don't even need this else there. Actually, if it's less than 0, we need to go negative p. Yeah. So it's kind of confusing here, so just make sure that this is implemented correctly. And this will just return the string that we need to add to our payload. Yeah. So pl equals move from tape to plt fgets. Cool. After this, we want to read it. So to read, we need to read and then go to the right. Read and go to the right. Read and go to the right. Let's just make another function to do this real quick, just to increase the simplicity. Def read. So this will just read a word, and this will just return this. And just to make sure that we go back to the address. We don't want read changing our pointer. Let's go back. So let's go ahead and add this. And while we're at it, we also have to write stuff. So let's just do this now. And yeah. And actually, to make it more general, this is really not necessary, but you can write in bytes just to make it a more general function, I guess. Okay, great. So then we're going to do pl, let's suppose we 4 bytes. And then we gotta send this payload. So we do, we have to start a, okay, let's go ahead and remote pwnable.kr, and I believe the port, I forgot what the port was, 9001, okay. Alright, so we start a remote, and then we send PL as a line. And actually, Actually, let's check to make sure that before we send stuff, we have. Let's just try this one real quick. Okay, so we have some text here. We don't want to send before that. Let's go ahead and receive the text. So receive line, and there, it looks like there's two lines. There are two lines there, but we, yeah. So let's just okay. Then we're gonna send the payload over, and then we got to read it. So it's going to obviously output back 4 raw bytes, and that's not pretty for us. So we want to change it to something that we can read, and fortunately for us, there is something. So we can get back the absolute address of fgets. There's a method of int called from bytes. It's very nice. We're going to receive 4 bytes, and byte order is going to be, and this is from bytes is really nice because you can specify the order. So for example, little endian or big endian, and it's not going to be assigned. All right, and let's go ahead and print what we get out of that, just to see what we're doing. Okay, so I'll print the address, absolute value address of fgets, and now let's calculate the address of libc base. That will be simply the absolute value of fgets minus the offset of fgets. That's simple enough. Let's go ahead and print that as well. Let's just move that there. Alright, and okay. After this, we can also go ahead and just calculate the absolute value address of gets in system that we're going to overwrite functions with. So gets is libc base plus the set of s. Pretty simple. I'm going to print that. And finally system. Probably could have done that a little bit more elegantly, but it's fine. Okay, so now we have gets and system. So let's just check if this works real quick. Yeah, let's check if this works and see if we read anything back. So. Alright, this is Python version 3. Oh, what did it do here? It did do X. Same to me. Okay. Oh, great. So we see we got an address of fgets and we got an address of the libc base. The libc base is at F7555000. And from this we determine the address of gets and system. Now I really don't know if these addresses make sense. I guess they kind of do. I'm not completely sure though, to be honest. But what we can do is just run it again. Okay, and we see that the addresses are different now. The libc base originally was at F7555, now it's at F75B600. So clearly there's it's kind of random where the position is, which is exactly why we need to read the value of fgets to determine the libc base. Okay, great. So So now that we see that this works, we are ready to do the rest of our magic. So first we have to add to our payload a little bit. Our payload is right here. So our pointer is currently moved to fgets. We've read. Now we want to write to fgets. Remember, fgets needs to be replaced, I believe, with I should have seen this right here with system, because memset was gets. So to replace with system, in our payload we just have to add a write 4 bytes, right? And then down here we have to send a separate line packed into pack system. So this will put system down here. This will write system to fgets, the plt and fgets. After this, let's do. We have to move now. Let's move from fgets in the procedure lookup table to memset. Memset is the next plt that we need to edit. So, okay, and we want to overwrite memset with yes, I believe. Yeah. Finally, we want to. Oh, I didn't write that yet. I need to write. We should write. And finally, we want to move from memset to our last one, which, if I remember correctly, yeah, it's put. It's the one we're going to initiate with the dot. And we're going to write 4. And we're going to write it with, I think we're going to write it with main. And main was defined way above, way early, first thing right here. Okay, great. Okay, after this, we have to actually start our kind of chain by just adding this dot. This dot will cause the dbf function to call putchar, which has now been edited to main. The main will run through. It will get our input, and then it will run system on our input. So we have to supply some input to that. So let's do sends, and we're going to send, of course, the command to start the shell, which is been sh. Right. So finally, we're done here, and if we do get a shell, we want to be able to interact with it. So we just call the interactive methods. So this should work. Let's go ahead and run it to see if it does, and let the steam out. I guess that's possible. If that's possible for software. Okay, so it seemed to run. Notice that we got this, even though we've already run it. So let's see if we do have a shell. Ooh, okay. Ah, so we do. We got access. This is great. So let us now open our flag. Ooh, brainfuck? What a weird language. So now, of course, you can go ahead and copy this into the flag box. Oh, I'll get first. Oh well, great. So we have seen here an very interesting exploit. Oh, of course, there's no exploit there. So we have seen a very interesting exploit involving a program that was supposed to do some pretty interesting stuff, which is like run programs. I'm assuming that are only composed of those, like what, 6 or 7 commands. But because there was no bounds checking on the memory there, we were able to really exploit it, because the pointer we can write to the pointer, we can change the pointer, change the location of the pointer, and as well as writing and reading the value at the pointer. We had to read the value from the pointer to really get the addresses of the functions that we wanted to write. For example, gets and system. And we needed to write the pointer, obviously, to overwrite, do the overwriting itself. So for this one, we had to construct quite an interesting payload here, and we wrote some functions to help us simplify, make it a little bit easier on the eyes, and then we sent the addresses that we wanted to overwrite, which were of course calculated from the result that we got from the read. And yeah, so we got the shell there, looked pretty good, we got the flag. So I hope you enjoyed this video. It's been pretty long, didn't mean for it to be this long, but if you're still watching, I hope you enjoyed, and I hope you saw also the merits of using IDA Pro. We'll be doing more of this in the future, so stay tuned, and I'll see you next time.